Welcome to PSR Tech Tutorials, where we simplify technology one step at a time. Don't forget to like, share, and subscribe to stay updated with our latest tech courses. Welcome to machine learning, where data transforms into intelligent insights. This path bridges the core concepts of algorithms with tomorrow's innovations. Designed specifically for newcomers, it breaks down complex logic into clear milestones. Embark on a beginner-friendly journey to master the future of technology, step by step. Let's look at what machine learning actually is, how it differs from traditional coding, and why it is such a big deal. What is machine learning? At its core, ML teaches computers to learn directly from data, meaning there is no explicit programming needed. Instead of humans writing down every single rule, we feed the computer examples and let the model discover the underlying patterns entirely on its own. Traditional programming. To understand the difference, think of traditional programming as a strict manual. Humans write explicit, line-by-line rules, and the computer simply follows them exactly, leaving absolutely no room for adaptation. Machine learning. With machine learning, the process is flipped. Humans provide the raw data, and the model figures out its own rules, allowing it to adapt and automatically improve over time. Why it matters. This shift is incredibly important because it scales to levels of complexity that no human could ever hand code. It is the very engine behind everything from everyday email spam filters to advanced medical imaging systems. Let's see how AI, machine learning, generative AI, and AI agents are different from one another, and how they build on top of each other like layers. AI, artificial intelligence. This is the biggest bucket. It is the broad field of making smart machines that can copy human intelligence, like how a human thinks, sees, or solves problems. ML, machine learning. A smaller part inside the AI bucket. Instead of a person writing strict rules for the computer to follow, ML lets the computer look at lots of data and learn the patterns on its own to get smarter over time. Generative AI, a special type of machine learning that has become very popular. Traditional ML is good at looking at data to make a guess, like checking if an email is spam. Generative AI goes a step further and uses what it learned to create completely new things, like text, realistic images, and music. AI agents, the smartest layer built on top of everything. While generative AI waits for you to type a prompt, an AI agent is like an independent assistant. It can look at a situation, make its own plan, use digital tools, and take real action to finish a goal for you without needing human help at every step. Let's dive into the three main types of machine learning to understand how systems actually learn. Supervised learning. The model is trained using labeled examples, acting like a student with an answer key to make accurate future predictions and classifications. Unsupervised learning. Here, the system is given raw, unlabeled data and must find hidden patterns, groupings, or structures completely on its own without any preset answers. Reinforcement learning. This approach relies on an agent interacting with an environment, learning to make the best decisions through trial, error, and feedback rewards over time. To understand machine learning, we need to look at its core building blocks. Data. This is the raw material. The more quality data we provide, the better the model performs. Features. These are the input variables the model learns from, such as a user's age, income, or clicks. Labels. This represents the correct answer or output that the model is actively trained to predict. Train/test split. Finally, we separate our data into distinct sets, one part to build the model and the other to evaluate it. Every machine learning project follows a repeatable, four-step pipeline that is continuously refined until the model performs reliably. Collect data. We start by gathering raw inputs from various relevant sources, such as databases, APIs, or physical sensors. Pre-process. This raw information is then cleaned, normalized, and properly encoded so the model can easily consume it. Train model. Next, we fit the chosen algorithm to the training data and tune hyperparameters to optimize its learning. Evaluate and deploy. Finally, we test the model's performance on entirely unseen data before officially shipping it out to production. Let's take a closer look at the different learning styles in machine learning. We will explore how supervised, unsupervised, and reinforcement learning actually work, and see exactly where each method shines best. Let's look at supervised learning. This simply means teaching a computer by showing it examples that already have the answers attached. This method handles the two most common jobs in machine learning. The first job is regression. This is used when you want the computer to guess a specific number. For example, trying to predict the exact price of a house or how much of a product people will buy. The second job is classification. Instead of guessing a number, this is used to put things into separate buckets or categories. For example, sorting emails into spam or not spam, or checking if a medical scan is healthy or sick. To put it simply, if the computer is guessing a number, it's regression. If it's picking a category, it's classification. Unsupervised learning is about finding hidden patterns in data when we don't have labels or predefined answers. Clustering groups. Data points that share similar features. For example, it can automatically group customers into segments based on their behavior, even if we don't tell the system what those groups should be. Association. Association looks for rules and relationships between items in a dataset. A classic example is market basket analysis, discovering that people who buy bread often also buy butter. Together, clustering and association help uncover structure in raw data, giving us insights we might not see on our own. Reinforcement learning is a way for machines to learn by trial and error. An agent tries different actions, and it gets rewards for good choices or penalties for bad ones. Over time, it learns the best strategy by maximizing rewards. Game-playing AI. Systems like AlphaGo and chess engines mastered complex games by playing millions of matches against themselves, improving with each round. Robotics. Robots use reinforcement learning to walk, grasp objects, and navigate environments, training through countless simulated attempts before working in the real world. Autonomous vehicles. Self-driving cars rely on reinforcement learning to make split-second decisions, like when to change lanes, brake, or choose the best route. In short, reinforcement learning teaches machines how to act in dynamic situations, learning from experience just like we do. Let's look at some of the most popular machine learning algorithms. Linear regression. This algorithm predicts numeric outcomes along a straight line. It's one of the simplest methods, easy to interpret, and very fast to train. Decision trees. Decision trees split data using yes or no questions. They're highly interpretable, which makes them easy to explain to non-technical stakeholders. K-means. K-means groups data into clusters based on similarity. It's widely used in customer segmentation, helping businesses understand different groups of users. Neural networks. Neural networks are inspired by the human brain, with layers of interconnected nodes. They're the foundation of deep learning and power modern AI breakthroughs. Together, these algorithms form the building blocks of machine learning, from simple predictions to advanced AI systems. Let's look at some of the most widely used machine learning algorithms. Logistic regression is a simple yet powerful tool for binary classification, predicting probabilities between two outcomes. Random forests improve accuracy by combining many decision trees, making them more robust against errors and noise. K-nearest neighbors classifies data by looking at the closest points around it, using the idea that similar things are grouped together. Naive Bayes applies probability theory with the assumption of feature independence, making it fast and effective for tasks like text classification and spam filtering. Together, these algorithms form the backbone of practical machine learning, powering everything from predictions to everyday applications. Machine learning offers a wide range of approaches. Supervised learning covers classics like regression and decision trees. Unsupervised learning includes clustering and dimensionality reduction. Ensemble methods combine models for stronger performance. And advanced techniques, like deep learning and reinforcement learning, push the boundaries of what's possible. Together, these categories form the foundation of modern machine learning. Imagine you are trying to bake a world-class cake. It doesn't matter how expensive your oven is. If you use bad ingredients, you'll get a bad cake. Machine learning is exactly the same. We have a saying for it: quality in, quality out. The data you feed into a computer model matters just as much as the math behind it. If you put garbage in, you get garbage out. To build a great model, you need great data. Here is the simple, three-step process we use to get that data ready. Step 1 is to select. Think of this as cleaning out your pantry. Data sets are full of extra clutter and random noise that you just don't need. In this step, you pick out only the most important ingredients and throw away everything else that might confuse the computer. Step 2 is to transform. Raw data is rarely ready to use right away. It might be the wrong size, the wrong format, or written in a way the computer doesn't understand. In this step, you reshape, clean, and prep the data so the computer can read it smoothly and correctly. Step 3 is to create. This is where the real magic happens. Instead of just using what you already have, you combine your ingredients to make something brand new. Making these new, smart data pieces is usually the absolute best way to make your computer model way more accurate. Conclusion. And that's it. By selecting the right data, transforming it into the right shape, and creating new insights, you give your model exactly what it needs to succeed. One of the most important concepts in machine learning is the balance between underfitting and overfitting. Underfitting. When a model is too simple, it misses the signal entirely. This leads to high bias and low variance, performing poorly on both training and test data. Just right check. The ideal model finds the balance. It generalizes well to unseen data with just the right level of complexity. This is the goal of every machine learning project. Overfitting. On the other end, a model that's too complex memorizes noise instead of learning patterns. It shows low bias but high variance, great on training data, yet failing on real-world tests. When we build a machine learning model, we need ways to check how well it works. That's where evaluation metrics come in. Accuracy. This tells us the percentage of correct predictions. It's simple, but not always reliable if one type of data is much more common than the other. Precision and recall. Precision shows how many of the positive predictions were actually correct. Recall shows how many of the real positives we managed to find. These are very important in areas like fraud detection or medical tests. F1 score. The F1 score combines precision and recall into one number. It's useful when the data is imbalanced because it balances both sides. Confusion matrix. This is a table that shows all the results, correct and incorrect, so we can see exactly where the model is making mistakes. By looking at these metrics together, we get a full picture of how well a model performs, not just whether it's right most of the time. Deep learning takes machine learning to the next level. It uses neural networks with many layers, stacked together like building blocks. These layers allow computers to learn complex patterns and make powerful decisions. Deep learning is the engine behind modern AI breakthroughs, from recognizing images and understanding language to driving innovation in countless fields. It's the technology that makes today's smart systems truly intelligent. Machine learning and deep learning are closely related, but they work in different ways. Machine learning. Machine learning learns patterns from data. It works best with structured data like tables and numbers, but it often needs human help. Experts design features and guide the process. Common methods include regression, decision trees, support vector machines, and clustering. Deep learning. Deep learning uses multi-layered neural networks. It shines with unstructured data like images, text, and audio. Instead of relying on manual feature design, it automatically extracts patterns from raw data. This is what powers modern breakthroughs in vision, language, speech, and even self-driving cars. In short, machine learning is great for structured problems, while deep learning unlocks the power of massive, unstructured data. Let's see how AI, machine learning, generative AI, and AI agents are different from one another, and how they build on top of each other like layers. AI, artificial intelligence. This is the biggest bucket. It is the broad field of making smart machines that can copy human intelligence, like how a human thinks, sees, or solves problems. ML, machine learning. A smaller part inside the AI bucket. Instead of a person writing strict rules for the computer to follow, ML lets the computer look at lots of data and learn the patterns on its own to get smarter over time. Generative AI, a special type of machine learning that has become very popular. Traditional ML is good at looking at data to make a guess, like checking if an email is spam. Generative AI goes a step further and uses what it learned to create completely new things, like text, realistic images, and music. AI agents, the smartest layer built on top of everything. While generative AI waits for you to type a prompt, an AI agent is like an independent assistant. It can look at a situation, make its own plan, use digital tools, and take real action to finish a goal for you without needing human help at every step. Machine learning is transforming the way every sector operates. In healthcare, it supports faster diagnosis and smarter patient care. In finance, it strengthens fraud detection and drives algorithmic trading. In education, it enables personalized learning and smarter assessments. In transportation, it powers autonomous vehicles and optimizes routes. In manufacturing, it predicts equipment failures and improves efficiency. And in retail, it delivers personalized recommendations and streamlines supply chains. From hospital wards to trading floors, machine learning is reshaping industries everywhere, making them smarter, faster, and more efficient. Machine learning is transforming healthcare in powerful ways. Diagnostic imaging. AI systems can analyze medical scans with remarkable accuracy. For example, they detect diabetic retinopathy from eye images with over 90% accuracy, matching or even surpassing human specialists. Drug discovery. Machine learning speeds up the search for new medicines. What once took more than a decade can now be reduced to just a few years, helping bring treatments to patients much faster. Predictive care. By spotting patterns in patient data, ML models can flag high-risk individuals before symptoms get worse. This allows doctors to step in earlier, improving outcomes and lowering costs. Together, these advances show how machine learning is making healthcare more accurate, efficient, and proactive. Machine learning is reshaping the financial world. Fraud detection. ML models can scan transactions in milliseconds, spotting suspicious activity instantly. Visa alone blocks over $25 billion in fraud every year using these systems. Algorithmic trading. Trading decisions that once took minutes or hours are now executed at machine speed. ML algorithms react to real-time signals far faster than any human trader, giving firms a competitive edge. Risk management. Machine learning also helps banks and investors manage risk. By modeling exposure across portfolios, it reduces systemic risk and improves stability in real time. Machine learning is driving big changes in transportation. Autonomous vehicles. Self-driving cars use ML to process huge amounts of sensor data every second. They perceive the environment, make decisions, and drive in real time. Route optimization. Companies like UPS save millions of gallons of fuel each year by using ML to plan smarter routes. This cuts costs and reduces emissions at the same time. Predictive maintenance. ML models can spot signs of equipment problems before they happen. That means fewer breakdowns, less downtime, and safer, more reliable fleets. Together, these applications make transportation safer, greener, and more efficient. Machine learning isn't just for industries, it's part of our daily lives. Recommendations. Streaming platforms like Netflix, Spotify, and YouTube learn what we enjoy. In fact, most of the content we watch or listen to comes from personalized recommendations powered by ML. Smart assistants. Voice assistants such as Siri, Alexa, and Google use ML to understand natural language in real time. They handle millions of queries every day, from setting reminders to answering questions. Spam filters. Email services rely on ML to protect our inboxes. These systems block nearly all spam, over 99%, before we ever see it. From entertainment to communication, machine learning quietly makes everyday experiences smarter, faster, and more convenient. As machine learning grows more powerful, we must also face its challenges. Bias and fairness. Models can pick up human prejudice from the data they're trained on. This can cause real harm in areas like hiring, lending, or criminal justice. Privacy. Protecting sensitive personal data is essential. With more regulations and ethical concerns, privacy is becoming a core responsibility in ML. Explainability. It's not enough for a model to be accurate. We need to understand why it makes a decision. This is critical in healthcare, law, and other high-stakes fields. The path forward. The future of ML lies in building systems that are powerful, transparent, and responsible. Technology that earns and keeps human trust. Ethics and accountability will shape how machine learning impacts society in the years ahead.